Good morning students. Today's topic is decimation in frequency fast Fourier transform algorithm. So to reduce the computational complexity of the direct computation of DFT, we are using these fast Fourier transform algorithms. Up to now you have seen DIT-FFT algorithm, that is the decimation in time fast Fourier transform algorithm. So here this is the another approach, that is decimation in frequency. So here in the previous case, that means in DIT the decimation is in the time domain. Now here in this particular approach, the decimation is in the frequency domain. So that means take the here DFT formula. So that DFT formula is x of k is equal to summation x of n wn power kn. Split this equation into two summations like n0 to n by 2 minus 1, and also here summation n is equal to n by 2 to n minus 1. So now here in these two summations, so take the second summation, in that substitute n by 2 plus n in terms of n. So now here if you substitute n by 2 plus n in the place of n, here the summation limits are changed from 0 to n by 2 minus 1 instead of n by 2 to n minus 1, and of course x of n becomes x of n plus n by 2. This one is wn power k n plus n by 2. Now here expand this one, that means wn power kn into wn power k n by 2. So now wn k n by 2 is independent to the summation n variable, therefore take it outside. Now wn power k n by 2 summation n0 to n by 2 minus 1 x of n plus n by 2 wn power kn. Here if you observe, summation limits are same and then wn power kn is same. So if you common these summations, then you can get summation n0 to n by 2 minus 1 x of n plus wn power k n by 2 x of n plus n by 2 into wn power kn. Here wn power k n by 2 is nothing but e power minus j 2 pi by n whole power k n by 2. It gives e power minus j pi whole power k. Of course e power minus j pi is nothing but minus 1. Now minus 1 whole power k. So now here substitute that one in the place of wn power kn by 2. So then here x of k, that means is actually this one. We may write like this, right? If you split this equation so into two terms, we can write like this, right? That means x of k is equal to summation n0 to n by 2 minus 1 x of n plus minus 1 whole power k x of small n plus n by 2 wn power kn. So now here x of k is decimated into even and odd number samples. That means x of 2k is nothing but substitute in the place of k 2k and substitute 2k plus 1 in the place of k to achieve or to get the even and odd number samples of k, x of k. So that means here x of k we have one form, right? So different form from this one, right? So here take this one, here just split this x of k into two categories. One is the even number samples, another one is the odd number samples. This is the variation here when compared with the DIT-FFT. In the previous case, decimation is in x of n. X of n is decimated into even and odd number samples like x of 2n, x of 2n plus 1. But here x of k is decimated into even and odd number samples like x of 2k plus 1. So that means if you consider example n is equal to 8 in that, so here the even number sample means capital X of 0, capital X of 2, capital X of 4, capital X of 6. So odd number means capital X of 1, capital X of 3, capital X of 5, capital X of 7. So here we are separating these values, X of even values, X of odd values. So to find out those values from the K, so here you know that for even use 2K, for odd use 2K plus 1, right? And then here K values are from 0 to n by 2 minus 1. So now here in this equation, first substitute K 2K to get the even number samples. So X of 2K is equal to summation n0 to n by 2 minus 1 X of n plus X of n plus n by 2 Wn by 2 whole power Kn. That means here in the place of K, here substitute 2K. Minus 1 whole power 2K means minus 1 square is the plus 1. 1 power K means 1. Now Wn power 2Kn means we may write Wn by 2 power Kn. Here K values are from 0 to n by 2 minus 1. So now here coming to the odd number samples, that is X of 2K plus 1, substitute in the place of what is that K, 2K plus 1 here in this equation. So then minus 1 power 2K plus 1 gives the, here minus 1 power 2K into minus 1, minus 1 power 2K is the 1 into minus 1 means minus, then Wn power 2K plus 1 into n. That means Wn power 2Kn into Wn power here n. So now Wn by 2 power Kn into Wn power small n. So now this is the one here, X of n minus X of n plus n by 2 Wn power small n Wn by 2 power Kn. So here also K range 0 to n by 2 minus 1. So here if you observe these two equations, X of 2K, X of 2K plus 1. So let here G1 of n is nothing but X of n plus X of n plus capital N by 2. Then let G2 of n is nothing but X of n minus X of n plus n by 2 into Wn power n. So simply we may write X of 2K as summation n0 to n by 2 minus 1, G1 of n Wn by 2 power Kn, X of 2K plus 1 is summation n0 to n by 2 minus 1, G2 of n Wn by 2 power Kn. So here, so that means here these are nothing but, right? So this is the n by 2 point DFT. This one also n by 2 point DFT. So these are computed by these equations where G1 of n, G2 of n is nothing but this one. Based on these equations you can evaluate these two. Based on this we can evaluate X of 2K, X of 2K plus 1. So now coming to this computational procedure can be repeated through decimation of the n by 2 point DFTs X of 2K and X of 2K plus 1. The entire process involves, so here log n base 2 stages of decimation where each stage involves n by 2 butterflies of the type shown in the below. So here if you observe these two, so we are implementing these two in terms of butterfly diagram or signal flow graph. So here consider, so let it be this one is A and this one is B. This one here A plus B, here is A minus B Wn power n. So consider here Wn power r like that. So here let it be A plus B is nothing but capital A minus B Wn power r is nothing but B. How can you implement, how can you develop these equations? So in the signal flow graph, so see this, so A, B inputs. So here capital A is nothing but A, then plus B, this is nothing but summer, arrowhead is nothing but multiplier. So now here A plus B, now A minus B Wn power r means, so here is A, B is multiplied by minus 1, then A minus B here into Wn power r. So now B is equal to A minus B Wn power r. So based on this butterfly diagram, so we just implement here x of 2k, x of 2k plus 1 from the x of n, from the x of n. This is an example for the 8-point DFT. 8-point DFT, that means here n is equal to 8. Now here x of n is in the same order. So but here x of k is decimated, or the order is shuffled. So now here based on this, so we just implement butterfly diagram here. So to compute this x of 2k and x of 2k plus 1, that means here k 0 to 8 by 2 minus 1 means, so here 8 by 2 4, 4 minus 1 means 3, 0 to 3, that means 4-point DFT. Okay, so that's why here x of 0, here is a plus x of 4, right? Here x of 0 plus x of 4. Next one x of 1 plus x of 5, x of 2 plus x of 6, and so on. Similarly here x of 0 minus x of 4 into W8 power 0. So here this one is nothing but x of this one gives the x of 2k, that is the 4-point DFT of input is nothing but, right? So in the form, what is that? A minus b like that, a plus b like that, that means this one x of n plus x of n plus n by 2. Okay, so that's why here in this way you can develop. Then so just repeat the procedure, that means again here take this particular x of 2k, x of 2k plus 1, and again do it what is that procedure, repeated procedure. What is that? Again x of 2k is decimated, so like two different what is that DFTs. So one is the n by 4-point DFT, another one is the n by 4-point DFT. So in such a way, if you repeat the procedure until to reach the 1-point DFT, then you can get the signal flow graph like this. So here is a, after completing n by 2-point DFTs, do the n by 4-point DFTs, and then do the n by 8-point DFTs, right? So here in this example n is equal to 8, so this is nothing but 4-point DFTs, right? So now by combining these 4-point DFTs, that means, so split the each 4-point DFT into 2, one is the 2-point DFTs. Okay, right. So here if you observe x of n is here same order, then you can get the x of k. So order is shuffled, and then you can get the x of 0. Okay, so now here this is 2-point DFT or 2-point butterfly diagram, and this is 4-point butterfly diagram, and this is 8-point butterfly diagram. You can say like that one also. That means it comprises 3 stages. So first stage, second stage, third stage. That is complete reverse procedure of the DIT FFT. So in the DIT FFT, here is a, what is that? This type of butterflies are here, and this is here. So middle is the same. Okay. So now, so this is nothing but DIF FFT. Based on this also, you can get the same computational complexity as we have seen in the DIT FFT. Thank you.